This lab class we were doing the demo of musical notes. So, I wanted to show that how the musical note is going to look like in the spectrum. So, we will be doing the FFT of the musical notes. So, I will get the complete spectrum. So, have a patience to listen to this music again. So, we will see the thing. As you have seen the thing, the note has got increased. So, you will be seeing the spectrum of this. So, you will be seeing from the basic frequency here, it is approximately 200 hertz what it is kept, and then which goes up to 400 hertz. This will be my sa. You will be seeing re, ga, ma, pa, da, ni, sa. That is what you heard, and you can find out from the spectrogram what are the frequencies present in your music note or audio functions. So, today what we will do is as we are discussing about the filters in the theory. So, we will have a look at how we can use the FDA toolbox to represent what will the design what we can have with respect to. As I have been mentioning, FDA toolbox is going to be removed from the recent editions of it. I can give filter design also what it will be taking it. So, we will see that this is our FDA toolbox. So, earlier we have seen the thing that is I can have a response type, whether I want a low pass filter or high pass, I can select the thing. And then what kind of filter? So, FIR filter, either I can design the equiripple filter. So, if you click on this, you will be getting the various modes of the filters. If I want to use the window technique, I can use it, or any of direct implementation what you can see that you can select them. Okay. For the time being, we will select the window because we have comfortable with Hamming and then Hanning window in the theory. So, even the Kaiser window what you can select it. So, for the time being we will select first as the Blackman window. Then what happens? So, whether either I can specify my filter order or I will be going with the minimum order design. So, I will click on the here what it is shown is the sampling frequency is 48 kilohertz. So, we will bring it down to 8000, and this what we have seen in the last class is 1000 hertz what we will give it. So, I can it is not allowing me to design the minimum order. So, only it is giving me specify the order. So, I can specify as 30 is my order, and then I can view the response of it. So, we had seen in the last class that is this is my low pass filter what I am designing it, and samples what I have seen, this is my normalized frequency what it will be showing. So, that is my 8000 kilohertz is 0 to 2 pi what you will 0 to pi on the right hand side you will be seeing it, on the left hand side it will be 0 to minus pi the response will be. So, here it is pointing to 0 to 30 is the thing order of the filter what it has taken, this is the impulse response. In the time domain how it looks, frequency domain, in the theory we have seen it. So, now we are seeing how in the MATLAB what it is going to show it. So, the next one is I can do the design of the filter. So, we will design the filter. So, you have to hold on for a while. So, you will be seeing the response. So, what is it? I have given the cutoff frequency as 1000 hertz. So, you will be seeing that. So, when I map this to frequencies, this is going to go from 0 to 4000. So, normalized will be 4 what you will be seeing it in this case. So, this is my approximately 1000 hertz. So, which it should be giving me 3 dB cutoff what we say. So, you will be seeing that approximately it comes down to, this is my cutoff frequency, comes down by minus 3 dB, that is equivalent to 0.707 of the magnitude. So, you have to be careful when you are designing your filter, the output may be, what I say is amplitude may be modified basically. So, scaled version what you will be getting it. So, if you want, if it is 0 dB, the frequency is what I can pass, as you can see the thing is only up to 500 hertz. So, if you are doing anything beyond it, so you will be having the attenuation in the magnitude. So, you may have to compensate. Now, we will see that how the band stop frequencies are going to look like. So, here it has come down to approximately minus 80 dB, what we can say using the Blackman filter. So, it depends on how much down you want to come down. So, you can think of it and then use one of the filter. The order, if I increase it, as you will be seeing it. So, I will make it as 50 order filter in this case. So, we will see the Blackman filter itself. So, I can design the filter. So, now you will be seeing that as and when I am increasing the order of the filter. So, you will be seeing that the flat response is much more wider here, that is the pass band will be for more frequency, and this is my transition band, what we call it, from the 0 to whatever the delta is represented. So, it will be narrowing down as and when the order of the filter is going to increase. So, now I want to see that what is the group delay of this. So, I can click on it. So, you will be seeing that hopefully there is a trigger in your mind which is happening. So, direct form FIR filter is designed. So, the order is going to be 49, and then whether it is stable filter or not, what you will be seeing it says yes, and then it is a designed. So, why I am getting the group delay? It is a constant in case of linear filter. So, here the delay is going to be, although I have 0 to 49 samples, I should have had a delay of 50 samples since I have used the linear phase property. So, that delay, because I will be combining it, if you remember your structure, so which comes down by half basically. So, the constant delay of this filter is going to be 25 units. So, after that you will be getting it continuously your output if you are running for your real time applications. So, coming to, if you want to represent the phase of it. So, you are seeing that my phase has to be linear in the pass band, that is 0 to 1 kilohertz, what we have given the thing, this is cutoff frequency. So, which you are seeing that it is constant. So, if you want to represent your response is this, and then if you want to see the filter specification, you can go and then see that this is how my cutoff frequency low pass filter what I have designed. So, like this you can go design your high pass filter or band pass or band stop. So, we will see one band pass filter specification. So, you will be seeing that there will be two cutoff frequencies, that is FC1 and then FC2. So, these are the two things what you have to provide. So, as usual we can say that 8 kilohertz what I will take as my sampling frequency instead of 48, and then I will say my low frequency I want up to 400 hertz, which has to be eliminated, and then here I can give it as 3200 hertz. That means I want to allow frequencies between 400 and 3200 hertz, and then rest of them have to be eliminated. So, I will design the filter here, same Blackman window I am doing it. So, this will be the response what you can see it. So, what is it? So, 400 hertz is going to be this thing somewhere here what you will be getting it, and then this is 3000 approximately 200 what you will get the thing. So, this is what the design. So, if I change my filter to Hanning window, so you will be seeing the response what is the thing is going to happen. So, you are seeing that there are ripples what you will be seeing it, and then your response is going to vary. So, when you view this is what you will be seeing in the time domain, how the Hanning window looks like, and then this is the frequency domain. So, you will be seeing that your magnitude, your ripples will be somewhere here, that is minus 20 dB or whatever you will be getting it. So, that is what it says. Main lobe width is minus 3 dB in this case, you will be seeing it. Okay. So, these are the you will be analyzing these things. Maximum relative side lobe attenuation, what it says is minus 31.5 dB. So, somewhere here what you will be getting it below that. So, this is how you can play with your design thing, and then you can use it in your filter design. So, you can use FIR 1 or FIR 2 to do the design, or these are the coefficients. One of the thing what you have to do is, if you are using it for Code Composer Studio, so you will be seeing there is a IDE generation of coefficients. Any other platform, if you want to use Xilinx platform or HDL code, you want to generate it, or C header file, if you want to use the C code, you can generate using that, or I will put it as Code Composer Studio what I want to generate my coefficients with. So, I have to specify the header file, C header file, and then I will be getting here it is numerator, and the length is defined with BL, and then export what is suggested. What it says is sine 32-bit integer, what you export it as, that is what it is showing. So, and then I can specify the DSP board also, select the target for which I am generating it. So, or I can specify what I want it to be exported as. I can export it as signed 16-bit integer, or I can specify any other format. I want unsigned or unsigned 32-bit or signed 8-bit integer, depends on hardware which one you are using it. For us signed 16-bit is enough. So, I have chosen signed 16-bit integer in this case. And then if I call it as a generate, you will be seeing that it is going to generate, and then it gives the name as FDA coefficient. So, we can save it. So, I will be saving it in the documents because I have lot of things and downloads. So, better to save it here. So, you will be seeing that it is saved as star.h file. So, that is FDA coefficients.h what it will be storing it. So, we will go and then look at the values of it. So, in the documents file what I have stored it. So, you will be seeing that FDA coefficients is stored here .h file. So, if you see the format here, so what is it? It is filter coefficients, C source file what it is generated, and then from filter design and analysis toolbox and MATLAB whatever version signal processing toolbox what it has used is 8.5, MATLAB registered what it says, okay, and generated when, date and everything. So, you will be seeing that what is the filter you have generated, it is FIR filter, direct form FIR what it says, and the filter length is 51 because we gave order as 50. So, it will be generating the odd one, n plus 1 what it will be taking it, 51 is the order, and linear phase it is using type 1. So, if you want to change and other things you can go and then look at the manual and then you can do that. So, it says that filter coefficients were truncated to fit specified data type because we gave signed 16-bit. So, you will be seeing that BL is my length of the coefficients, and then you will be seeing the values of these coefficients here. So, it is from 0 minus 3. So, you have already seeing that it has taken care of truncation of the values in this format, in the fixed point format what I have given. Okay. So, this you will be using it in your Code Composer Studio to run your FIR filter applications. So, this is one thing. So, we will see how one can run in MATLAB itself. So, we can close this, and then what I will do is from the FDA toolbox I will be coming out of it. If anybody wants to see rest of the thing, so you will be seeing FIR filter, band stop or high pass filter one can design depending on your application. So, coming back to this thing, I have you can one by one run and then check it in the MATLAB.m file what you can generate and then do the thing. So, here usually I ask my students to generate a GUI for it will be easy to show that what is the filter they are using it and then how I can modify. So, in this case as a demo I am showing you this one of it which is developed. So, I will be going into this and then running it. So, you will be seeing that GUI is getting generated. So, now I have to specify here filter type what I wanted. So, we will see that I want FIR filter, we were trying it, we can do that, and then what is the response type what I want, whether I want a low pass response or a high pass, band pass or band stop. So, since we have done the low pass and then band stop design, we will take up here band stop. So, now what is the thing is usually why we use filter, in this case we are going to eliminate the noise. So, we will play the original wave file and see what I will be getting the output as. Play.
Remember, the force will be with you always.
Okay. So, this is the original audio speech file what you heard it. Now, we will say when the noise is added, how does it look like? So, there is a single tone noise what has been added to the speech and then which is fed as input to your filter. So, that is what it says, which tone has been added is 2100 hertz as noise is loaded into this. Now, we can play the filtered output. So, you will be seeing it.
Remember, the force will be with you always.
So, this was a single tone, what in terms of frequency what you are seeing it. So, approximately 2000, although it says 2100 hertz. So, you are seeing as a peak at 2500 and rest of it is vanishing, it is not staying. So, your speech magnitude filtered output what it showed and then went off. So, if you want to design an IIR filter, so I can give this, I can select a low pass filter IIR filter. So, it will be saying that some of the speech file with noise sine tone what it has added is 3750 hertz, which is going to be eliminated since we have seen the original already. So, we will hear for a change. So, if you are keen in observing the note, so you will be seeing the difference between 2100 and then 3750 hertz. Okay. Now, you play the same filtered output.
The force will be with you always.
So, you have seen the peak frequency which got added has got changed to 3500 approximately in the thing. Scale has not been normalized, I have expanded the thing. And what was the output? So, this eliminates the higher frequency component present in the thing and then it is allowing the speech to come out as clean. This is how what you will be experimenting with FIR and IIR filter together, that is it is GUI. Otherwise, you can run the code in MATLAB, create a .m file and then you can run them also. So, that is what one of the example what we have seen using the MATLAB filter. So, we will see in a while now. So, if you want to save or whatever it will be showing. So, we said that our sine generation using the DDS we had seen in the MATLAB. So, we will see in our DSK 6713 board, TI board as I have been mentioning it. So, how it is going to generate the sine wave. So, this is the C code what we have written. So, we have to use a library function and then the math function, and we are defining my length of the thing as 256, and we are keeping the rest of the code what we had used in the MATLAB function. So, if you correlate the equations, it remains the same thing. So, your desired frequency is 1000 and then the sampling frequency amplitude is 32,000, and then pi in this case we have to define, because there is no built in pi value in this case like in MATLAB. In C, as you know, you have to specify that, and then we have given the phase increment here and sampling frequency chosen as 48,000. So, I can generate both out 1 and then out 2. So, what is this out 1 and out 2 we will see in a while. So, one thing one has to keep it in mind when you are using the board, if you declare them as global variable, then you will be able to see their output. So, if it is a local variable, so you may not be able to plot them. So, that is the reason why output is kept as a global variable. Then we will be using the equation for I is equal to 0 less than I less than n, like even in MATLAB we did the thing. So, we will be doing the phase increment, and then what is with is desired divided by Fs what we have it. Desired is 1000, Fs is 48 kilohertz what we have used it, and then increment the phase. So, we are checking if phase is greater than or equal to 2 pi. So, if it is so, then we will be subtracting it with 2 pi minus we will be subtracting with 2 pi. So, we are including as a modulus 2 star pi operation in this line. Then what we are calculating, first one is the output 1 of I. This is magnitude multiplied by sine function what we are calling with the phase. So, scaled what we call it as L in output, and then we can feed it as a left hand sine one side and then the other one can be cos. So, you will be seeing that output 2 is given as amplitude into cos f with respect to phase what you have calculated here. So, when I these are the .c file what I am showing it as a main.c. Now, one of the thing is automatically when you open the new what we call it as give it as a new CCS project, if I select it. So, it will ask me what is the file name I wanted. So, I will call it as here in this case sine DDS, because I have given underscore there. Then it will ask me whether I want the executable. We will say yes, and then what is the family I am going to choose is C6000, and then we have given DSK 6713. If you are using the board, then I have to use Spectrum Digital DSK EVM EZDSP onboard USB emulator. So, and then you can give finish, then you will be seeing that your main.c along with it is going to be opened. So, here you can write your code and then run the thing. So, for the and then it will show this is the active debug folder or project which is selected. So, for because we have already written the code, so you can go and then insert it. So, I will be selecting this as my active code to be run in this case. So, then I will select. So, if I do this, it will be doing the compilation and even the build is going to be done in this. So, if there is any error in the thing, please go and then fix them. So, otherwise I can go directly for debugging. Then what happens, it debugs and then it is loaded onto the processor. So, you are seeing your cursor has entered into the main function. So, we will see that we will be going for the debug operation. So, you have this has to come when you are doing it. It says it has used Spectrum Digital DSK EVM DSP onboard 671X, what is the thing taken, and then it has entered the main function, and then interrupt what it is going to have is C underscore interrupt 00, it will be going into the boot, that is the entry point for the thing. So, to see that my output is coming out correctly, so if I run completely, then I may not be able to see whether my output 1 and then 2 are sine and cos functions. What I put is a breakpoint here. So, if you double click on it, it clears it, and then if you double click again, it is going to put a breakpoint. So, we will run this code and then you will see that it stops here. Now, what I have to do is see whether I am getting the sine wave generated correctly or not. So, I will be going to the tools and then I will be selecting a single time graph. So, I have to specify what is my length of it. So, we said 250, and then my output data type what I have declared is float. So, I can use 32-bit floating point, and then I will be giving this start address as output 1. So, then if I give the thing, so you will be seeing that your sine wave has got generated using the DDS method. So, if you want to again plot one more graph, that is single time I will call it. So, this also is going to be 250, and then this again what I have is a floating point, 32-bit floating point. So, I want to see my output 2, whether I am getting the sine wave. Sorry, you will be seeing that this is the single time, this is what you have it, the other one is shown here. So, you will be seeing that this is starting from 0 what you are having it, whereas your cos file you will be seeing that it starts from 1, which is in this case 32,000 is the amplitude what we have taken. So, that is what it is showing, and then it is repeating. So, if you want to see their FFT magnitude, whether you are generating the correct this thing frequency is getting displayed or not, I can select the FFT magnitude. So, I will be acquisition buffer again I will be taking is a 250, and then what I have is a 32-bit floating point. So, I can give a start address is for one of it we will see, the other one you can see it yourself, output 1, and then what is the frame size we will be taking up spectrum analysis in little later classes. So, if you want you can change the order of it. So, I will give it as 10, 2 per 10 will be my order of the FFT. So, you will be seeing that this is how what it is represented, because 1024. So, if you want to represent in a lower thing, so to get 1 kilohertz, so you can multiply what is the magnitude of it. So, the value what you are going to get it is going to show, multiply with your sampling frequency into 1024. So, you will be getting what is the frequency what you are getting it. This is our K point where it is shown. So, if you want to change it, you can change your order of the filter and then see what output you will be getting, whether you will get the 1 kilohertz represented or not. So, this shows how we can use our DSK board using C function to generate sine wave. So, in the next class we will, in the next lab we will be seeing how to do the filtering after generating a sine wave, that is using IR filter in the oscillatory mode and using it to do the filtering with different low pass and then high pass. What we have seen in the MATLAB, same way we will see it in Code Composer Studio. Thank you.